Now we come to a new topic, angular velocity, and then find its relation to the linear velocity. Now let us try to understand one thing about translational motion. What happens in a translational motion? What happens? Velocity of all the particles remains the same. Fine. That's why the moment I say the velocity is, say, 5 meter per second, you immediately understand that the velocity of all the particles that are moving is 5 meter per second. So that becomes the characteristic of all the particles of the body, right? So if I say 5, any particle that you pick up out of all the particles that it has, for example, it is a brick, it is composed of infinite number of particles, and that brick slides. Okay, so this brick slides what happens? All the particles, say this particle or that particle or this or that or this or that, or all are moving at the same velocity. Fine. So my saying that it is moving at 5 meter per second or v meter per second makes a sense in the sense that if you pick any particle, it's moving at 5 meter per second. So fine. Okay, so so velocity becomes the characteristic of all the particles of the system, all the particles of the system. Correct? Do we get that? Fine. Okay, that is our translational motion. Okay. Now, let us say we have a rigid body like this, which has a fixed axis, shown by this green dotted line. Now let us pick up a particle. Which is, say, here, and
the axis can be taken anywhere.
Normally passing through the center of the mass, right? Normally, but not essentially. So you can take it anywhere, and this axis is fixed. Fine. This is a fixed axis, and the thing is rotating like this. Okay, it is rotating like that. So looking from above, it is anti-clockwise, correct? Now, a particle which is here, as it starts rotating, you will find it'll undergo a circular motion. Is it not? And it is true for all the particles, not only this particle, correct? Now, I come here, so a particle A kind of goes like that, and a particle B sort of goes like that, and say another particle, say C goes like that. Okay, so so okay, these are three particles taking three circular motions, and as it turns by one turn, as it takes one turn, so maybe I'll name them A, say B, say C, and as the whole thing takes one turn, they come back and rest at the same place. They come back to the same place. Now all of them have taken the same amount of time, but the particle C has traveled a longer distance than particle B, which has traveled a longer distance than particle A, and the time that they have taken is the same. So the velocity of particle C is more than the velocity of particle B, which is more than the velocity of particle A. So VC is moving at a greater velocity, which is moving at a greater velocity than B, which is moving at a greater velocity than A. Now, the way we have defined velocity in translational motion, that creates a problem here. Why? If I say, fine, this is 5 centimeter per second, then this fellow may be 7 centimeter per second, and this may be, say, 9 centimeter per second. Now, which velocity do I define? If I say 7, then I have to say which one is having a velocity of 7. So I'll have to say maybe the one that is 1 centimeter away. Maybe, right? Maybe the one that is 1 centimeter away is moving at a velocity of 7 meter per second. That which is 2 centimeters or 3, say, in this proportion, 7 by 5 centimeter away, so that will be having this velocity, and 9 by 5, 1.8 centimeter away will have this velocity. The higher the velocity, okay, and it's just 2 pi r, so you'll be able to understand what it is. Fine. So the way we have been defining velocity for our translational motion does not hold good for the rotational motion. Do we understand that? Okay, so in a rotational motion, the particles are moving at different velocities. They are moving at different velocities. So defining a single velocity does not work in the same way as it worked in translational motion. Do we get the point? It does not work the same way as it does in the case of translational motion. Correct? Now what do I do? Fine. And that is where we move ahead and define a different quantity altogether. Fine. So that's where we define a different velocity, and that velocity is called angular velocity. Now try to understand first of all the concept. What happens? Fine, they are moving at different velocities, but there is one thing that is common about them. And what is that? All of them have traversed. What is there that is equal for all of them? No, time is fine. That is the denominator. There is one more thing that is the same for them. The angle. The trajectory is fine. It is similar trajectory, circular motion, but the angle through which they have turned, that is the same, and that is 2 pi radian, 360 degrees. Okay, so fine, the outer one is moving at a higher speed, and in the sense that we have defined speed in a translational motion, right? But the angle by which they turn, that remains the same. So the angle by which all the three particles turn remains the same. That remains the same. In this case, it is 2 pi radians, is it not, for one turn? For one turn. Fine. That means the angle swept, the angle traversed per unit time remains the same. Is it not? Thus, the value of angle swept per unit time is a constant. Is a constant. Okay, it is a constant. Do we get that? So we must be defining something that is kind of radian per second, so that the moment I define it, it holds for all the particles. You understand the ease? You understand my ease of definition? That if it remains the same, I am on the same platform as I was here while defining the translational velocity. You understand that? Okay? Thus, we define the angle swept or the angle traversed per unit time as a measure of all the velocities, as a measure of all the velocities, as a measure of the velocity of, as a measure of the velocity of all the particles, right? We call this angular velocity. We call this angular velocity. We call this, let's take its name with respect, so I write it in capitals. Angular velocity. You are encountering it for the first time. Fine. And it is denoted by omega, small omega, denoted by omega. Yes? Doubts? Fine. In circular motion, what had happened, you know? Since there was only one particle that you were discussing, they told you it is that. Here, in case of a system of particles, it becomes an imperative. You understand? Here it becomes an imperative to define it. There it was not imperative. Okay? It was not. And when I was discussing that, I had told you, you'll understand better why we have introduced a term called angular velocity. Their velocity would have been sufficient because there was one particle and it was a circular motion moving always at the same distance, so magnitude of the velocity was always a constant. Here it becomes an imperative, and we should understand that. Now, this is a vector quantity. This has to be a vector quantity. You understand? And there comes a trouble. What is that trouble? If it is a vector quantity, what should be its direction? What should be its direction? Now it tells me, see, it is say rotating like this. Okay, so I am drawing a top view of this. Okay, I am drawing a top view of this. So I'll be drawing a circle which will be moving in a, which will be I'm still on the lookout for a perfect circle drawn by hand. Fine. So this is all traveling like this. Okay. This is say one of the particles. I am talking about say the point P. Okay. So I'm talking about point P. Okay. Fine. Now, how do I define it? Do I do it like that, or this, or this, or this? What? Now, immediately you come to know there can be infinite number of possibilities if I do that. So, keeping the angular velocity in the plane of the circle that a particle sweeps, okay, is very difficult. It is impossible. Impossible in what sense? It is, the whole thing is rotating. You put the vector there, and the vector after some time rotates and goes somewhere else. So how do I define that? Okay, it should be easily definable. So keeping this vector in the plane of rotation, makes it difficult to define, right? Difficult to define. So we won't do that. So I erase this. I don't do that. Then what do? Then suddenly it struck us, why not keep it perpendicular to the plane? Is it not? So it was decided, yes?
You can't just do that in physics.
So it is what?
Something just struck and just put it like that.
Yeah, that's how it developed, right? Yes. That's how it went up, yes. So it was decided to keep it perpendicular to the plane. Because why? It's a logical subject, that's how it has developed. You'll see so many things defined later. You'll understand how it was an afterthought. No? So many things happen in chemistry which are an afterthought. Any example? Any burning example? No.
DNA.
Afterthought. You went ahead, then you came back. Laws of thermodynamics. First law of thermodynamics came first. Second law of thermodynamics came later. And since we had defined it for a hell amount of time, suddenly we realized, no, there is something more basic. And we had simply no way out. And we came back and we said it is 0th law of thermodynamics. Yes. It is 0th law. And if one of you maybe come across a more fundamental thing, you will have to go to a -1. Okay? Uni-negative law of thermodynamics, sort of, to give it a. That's how the understanding develops. So yes, it was actually thought. It was decided. How do I define it? So it was decided to keep it perpendicular to, and if you understand it this way, then you understand that there is no arbitrariness involved in defining these things. That is also important. Otherwise, what happens? All your life you are in a tremendous khunnas. You are in a kind of, what? I was like that. I'll be under a tremendous kind of thing if I don't understand the logic. So the logic was this. And it was a very, very sound logic. Fine? It is a very sound logic. So it was decided to keep it perpendicular to the plane of motion, right? Now what happened? Now there are two perpendiculars, another trouble. So you say fine, this is how the object is traversing, okay, in a plane, and this is how it is traversing, and you want to keep it perpendicular. So which perpendicular, this or that? You understand the trouble? And then came a rule that will be through and through and through with you. It is called right hand thumb rule, and it has at least 200 different varieties of the same right hand thumb rule. Okay, at least 200. So it is to keep it perpendicular to the plane of the motion, and then but there are two perpendiculars to the plane, right? Perpendiculars in this case into the board, yeah, or when I'm looking from upwards, either below or along the axis up, okay? But there are two perpendiculars to a plane. So it was decided to use the right hand rule, the right hand thumb rule. And what is that rule? That rule is this: if something is rotating, if the rotation is like this, that means you keep the fingers of your right hand along the direction of rotation, then the thumb of your right hand will point in the direction of the angular velocity. This, you understand? So this whole thing is moving like this. So my thumb, so upward. So omega will be upwards.
Like current and magnetic field.
It will be. That's why I said there are at least 200 manifestations of the same rule. Okay. So you have to understand in which you are using which. Okay. So omega became this. This became your omega. Understand? This was your omega. Understand? In this case it was this. Right hand thumb rule. It says what? It says if the fingers of the right hand point in the direction of the motion, the fingers, the thumb of the right hand points in the direction of angular velocity. Of angular velocity. Fine. So by that convention, our angular velocity is up. It is up. Fine. For this, it's moving like that. This. If I turn the rotation, it will go down. If looking from up, it is clockwise, it will go down. This is also called right hand screw rule. If you take a right handed screw and its head pointing towards you, and you rotate it counterclockwise as it is rotating looking from above, that bolt actually opens up and linearly it moves towards you. So that is the direction. Okay, this is also called right hand screw rule. Okay, also called right hand screw rule. Okay. You understand? Actually, why right hand? Because there are also left-handed screws. They behave in the opposite manner. So you kind of do the opening motion as you do with the right-handed screw. It will start going down. Okay, so these are oppositely threaded. One is like that, they are like that. So it will go down. If you try to open it up, it will close. If you try to close it, it will open. Okay. Fine. Okay. So now we understand the need for defining a different quantity. We have been able to give it a direction. And what is the unit? So unit of angular velocity, unit, let me, so angular velocity is angle swept upon time taken, correct? On time taken, which is delta theta upon delta t, which is what? Which is radian per second, or you can say per second. That is the unit. Okay, that is the unit. Radian itself is unitless. It is L upon R, is it not? It is L upon R, ratio of two things. So unitless, but we name it like that. So in effect it is per second, right? Dimension wise it is, what is the dimension? T to the power minus 1. Because radius does not have any dimension, right? Now if you want, if the velocity is variable, what happens? As we did in kinematics, we take delta t to be very, very small, and then it becomes d theta upon dt is equal to omega. That becomes the instantaneous value, right? So instantaneous value, angular velocity is equal to limit delta t tending to 0, delta theta upon delta t, which becomes d theta upon dt. This is your instantaneous. This is your average. So here when I had defined it, it was an average quantity. So I can write it as omega average. Okay, that became equal to delta theta upon delta t. So let me summarize. Delta average is equal to omega average is equal to delta theta upon delta t, and omega instantaneous, I am writing inst, is equal to d theta upon dt. And we understand what d theta upon dt means very well from our kinematics, right? You have to hold that in mind.